Okay, hey everyone. My name is Rudy Hill, and I've been working as an FPGA engineer for the last 5 years. And today we're continuing our discussion of digital circuits. Um, so this is kind of all culminating in how to analyze and maybe at some point design your own CMOS circuits. And we're gonna in this video we're gonna kind of take everything that we've learned so far, basic logic, gates, transistors, all that, and we're putting it together. But I have to tell you something pretty important, and I thought ahead, and I already drew out the truth table. I already drew out the circuits. So let's talk about NAND. NAND, how does it sound like, right? And then you put an and in front, not and. So that's the only note I'll put here is that it's not an and. I'm gonna go through this. But to be honest, I think it's pretty straightforward. So this is symbol for it. It just has like this little dot here that kind of means not. Usually this all the stuff dots mean knots. And this is like an equal sign, and maybe it's not the best drawing, but basically this is equivalent to you have A and B inputs, you have an and then you have an inverter or a not. Go with C. Here's the truth table. So it's just an and, just completely inverted though. Basically, it's gonna be one for every case except for A and B are one. Great. And then NORs, very similar. We have an OR gate, and then we have a dot to say that it's a NOR, and it's the equivalent of an OR gate passed into an inverter. Great. So it's the same thing. Usually ORs, it's one everywhere except in this case where A and B are zero. So it's the outputs just backwards. So great. That's all you need to understand about NANDs and NORs. And at some point, maybe I'll make a video about XORs, XNORs, a bunch of other stuff. But for now, all we're trying to do, like I said, this has been the culmination of our learning here as we kind of move on to other topics and other problems that you might see in interview questions or just for fun, maybe for your own design. All of this is just a crash course, right? So we're just gonna get into this because it's gonna be obvious why I brought this up now. Um, so you know how I was talking about CMOS circuits? It has this complementary of you have a PMOS transistors here and NMOS, and we use it for an inverter, and it's maybe kind of like, okay, well, great, we can invert stuff, and maybe it's like why is it complicated? Maybe there's some other ways to do it. Um, I'm going to show you exactly a use case. So we're going to analyze the circuit. Instead of building it, we're going to analyze this. Um, so let's start with the truth table, shall we? So we're going to start with A, B, and yeah, we'll call this C. This output here, C. So yeah, let's go through. Let's do our basic truth table. So let's think about this. So let's consider the case where A and B are zero. Okay. What is it? So let's just kind of go through all these. So these A's and B's. I said this is the same A. This is the same B. We're basically using the PMOS and the NMOS parts of the circuit for this complementary pair. We're going to see what comes out with C. Okay, so what happens when um, A is zero and B is zero? So let's start with the top portion over here. So it's PMOS. So when you apply a voltage, um, it stops current going through source and gate, and when you remove voltage, it allows current to flow. So we'll use yellow to show current, but basically we have flow here and flow here, right? Cool. And then what about down here? So we have NMOSs. So what does that mean? So because it's 0 and 0, these are just not going to flow, right? So basically, because current's flowing in VDD is connected here to C, um, we're going to say that C is 1, right? Because it's connected to VDD, which is again a logical one in this case. Cool. All right, let's get rid of some of this stuff. Oops. This might be a pain. Yep, it's going to be a pain. So get rid of all this, but we know that this is a 1. Great. So now let's go through. 0 for A, 1 for B. So this means that we have current flowing through here, but it's being stopped over here. But it doesn't matter since this is a parallel circuit. The current is going to continue here anyways. This is going to be shorted together. Well, that's not the right terminology, but you know what I mean. C is connected to VDD. Let's look here. So in this case, the A portion blocked. B, current can flow, but there's nothing here, right? So that's just connected to ground. So basically, this is being blocked off. The circuit's being blocked off, so it's connected to the logical one and not the ground. Okay, great. So this is 1 once again. So make a note of that. Boom. Wrong color. Boom. Let's do the same exercise over here. It just, spoiler, it's going to be the opposite. But for 1, this is going to get blocked off here. Blocked, blocked, flow, flow. So it's the same logic as before, just the other way around. So basically, yes, for the series here, you need both of them to be open for the current to drain. And for this, like you can have either input allow voltage to flow. So the analog, it should kind of be coming clear like what's happening here. But we deduced here that this is 1. But now let's get to a very interesting case. What happens when A and B are 1? So for the PMOS here up top, when they're both 1, they're both going to be blocked because right, PMOS is an inverter, right? That's not the right word, but it does the opposite of what you want. And here for the NMOS, they're both 1. Current's going to be allowed to flow for both of these. So actually, C will now be connected to ground. So C is actually 0. Now you see kind of why I told you about this. This is very similar. In fact, it's the same truth table as the NAND. And now you'd be thinking, okay, Rudy, you did promise to show us how to make an AND gate with transistors. This is a NAND, but this is not exactly what we want. So how can we make this logically into what we want? So let's just move this truth table. So I'm kind of just showing you all these techniques and kind of throwing stuff at you. So right now, what we have is not A and B. So what can we do to turn this to A and B? Well, maybe it's kind of obvious. You knot a knot. Logically, if you knot a knot, they cancel out. And this is kind of why it's Boolean logic, but boom. So all we have to do is knot this. So we have to put an inverter. Well, we got to do it with a PMOS, sorry, with a CMOS circuit. So I'll show you how to do that. Um, so we'll keep that C. We're going to keep this drain voltage here into the circuit. It's going to be some sort of output as we ground. But yeah, how do we knot with circuits? How do we implement a knot? We'll use an inverter circuit, and you've already seen this. So we have the PMOS, we have the NMOS. I didn't do this right, but you get the idea. So we can say that C is not A and B, and D is not C. It's not A, B, is the A and B. So there you go. This is how we have created our AND gate. So this is what we've created. We have created this representation that you've probably seen everywhere. The AND gate. Cool. So there you go. I kind of showed you some basic circuits and how to implement logic. We're kind of off to the races, and as you can kind of see, this what is this going to be? Um, so you can probably guess. But I'll just kind of do the truth table, and you can kind of prove it out yourself. But let's use the same logic here. Let's call this C as well. I'll do A, B, and C. C. Okay. So once again, 0, 0. Okay, this is gonna allow current to flow, and this is gonna get blocked. Both of these, since they're parallel. 1. Okay, what happens when this B? Apologies. What happens when this B is 1? Okay, so now it's gonna block this off. Blocked. And now it's gonna actually allow this to flow as well. That's the only difference. And I'll kind of let you do this exercise. If you need help, let me know. But I think if you're a smart person, you can kind of figure this out pretty easily. This will be a 0. And with A, it's the same logic. It's going to allow the other side to flow. And then if they're both 1, all these will be blocked, and both of these paths will be opened. So that's also going to be a 0. And just to be cheeky, like, oh, look, would you look at that? We happen to make a NOR. We made a NOR gate. Okay. How do we make a OR gate? We're going to use an inverter once again. So I'm kind of speed running this, and there's kind of some shortcuts you can use, and I'm just showing you all this to be illustrative. But yeah, we have our P, we have our N. I didn't quite draw this right, but we have our D. We have our inverter, and I'll do what we did here, but we'll say that D. How did I write it here? which is not A or B. Actually, sorry. C is not A or B, and D is not C. Not it is not C. I'm writing this all bad, but um, there's a funny little joke there for anyone. I'll just use different notation just so you get familiar with it. But D is not A or B. I messed up again. C is not A or B. D is not C. D not C is not A or B. Is equal A or B. So there you have it. What we just created. Don't judge me on my art really quick. But we created an OR gate. So we created an OR, and then we created an inverter on that, and then we made an OR. So yeah, I think I'm pretty satisfied with this. The only thing I would mention, I will kind of show you a shortcut. We'll take this OR gate for example. We'll take the NOR part of it at least. And how can we quickly deduce the truth table? I got an idea. And we'll see if it works backwards or not. But pretty much what we're doing here. There's a little shortcut here. I'm kind of talking about this for myself. Because we have this thing in series, these kinds of things act as an and, right? Because you need both of these things. So we have a not A or not B. So I haven't really we haven't really talked about this, but we'll talk about it in the next video. But this is not A or B. So that's kind of how we know this. But maybe it's clear for this bottom one. We're talking about this case where it's zero. So it's like, when is it zero? It's zero when we have A. So one path is A and one path is B. So that's how we can look at the NMOS side. But we really want to know where those ones. So it's not A or B. So that's how you can analyze a circuit. So you can do the same thing here. So because this is in series here, we could say it's we're looking for a not A and B, which is actually what this is. We'll talk more about this. We'll talk about more about De Morgan's theorem, but that's kind of a preview. Unfortunately, a lot of these concepts are related, so I'm just kind of showing you early. Not that you need to know this right now. But it's kind of cool. You can kind of analyze the circuit in kind of any arbitrary circuit. Now, the PMOS and CMOS, or sorry, the PMOS and NMOS might not actually be the same. But we're assuming they're the same. If it's not, then you're going to have to analyze it in different ways, and that's kind of messed up. And just kind of as heads up, circuits are really designed as a NAND or NOR technology. These these things are actually have to be manufactured, and maybe we'll talk about it later in another video. But I'm just giving you the basic concept, basic logic here. So cool, good job, everyone. If you had a question, ask in the comments. If you found this helpful, give it a like, of course. Subscribe if you want to know more. There's not really much else to this. I'm pretty happy with how these last few videos have gone to teach. Maybe I'll throw it all together into one big video and I think if there's enough need, if there's enough demand for that, I don't really see anyone in the comments. I'm exaggerating. There's like one guy so far. Um, but yeah, if there's like a really big need, there's that project by Three Blue One Brown Manum. I know he doesn't maintain it, but I kind of like some of those Manum animations, or who knows? Maybe we could do something in Blender to kind of show some of this stuff. Because one thing I didn't really talk about was MOSFET technology, this metal oxide semiconductor. There's a lot to talk about. There's a lot of videos even online that you can check for yourself to kind of look at some of this stuff. But I just feel like a lot of people they talk. Maybe I'm monotone, but I think a lot of people online, I hate to say it, but they talk monotone. It's very unclear. They kind of don't give you a clear answer. But I'm hoping to kind of be more down to earth, and it's a kind of like a meme, but relatable. As someone who didn't really understand this to someone who did. So maybe that's helpful. So maybe I can answer at that level, maybe some misconceptions. Anyway, that's a huge rant. That's maybe a meta video, a video about the channel, kind of where this is going. But I am rambling. So, anyways, talk to you guys later. I have some more stuff planned.